let's get to it. Okay, today what we're going to talk about is your transformation. So what do we linear transformations is a big part of this course. So we've talked a lot about linear transformations. And one of the big things is we have if we have a linear transformation from Rn to Rm, then T can be represented as N by M. N by N. And we know how to build these things now. But what if the n-dimensional vector space and W was an n-dimensional space? Can we still and so the question now is, if you look at these matrices, specifically going from Rn to Rm, what if I just walk up to you on the street and just give you just a random n-dimensional vector space? And we see things like this, like polynomials, well, for n-dimensional degree n-1 or less, be an n-dimensional vector space, and W is some other n-dimensional vector space. And suppose we have a linear transformation here. Can we also get a matrix that represents this? So represent this return. And as you might suspect, the answer to this is yes. And actually, on some of the quizzes, I've given you some problems to look back and sort of build up. We did some kind of computations that do this kind of thing. But we're going to formalize this here and talk about how you do this in general. Of course, the idea behind this is to use coordinate vectors. And one of the big things of this is, literally speaking, if you have an n-dimensional vector space of real numbers, then it's essentially no different from this. And you can associate an element here with an element here just by looking at coordinates. Let's see how this works. So I'm going to paint the picture of how this works in general, and then I'm going to go back and patch this up with some examples. So here's my situation. So suppose V and W are of dimensions N and M respectively. And let's let B be a basis for B. and C, C1, C2, CM, the basis. Now, what allowed me to build a matrix from Rn to Rm? Well, because what's a typical element of Rn look like? It's just a stack of n numbers, and I make it go through a stack of n numbers, and I use an n by n matrix to do this, and I can set up system equations to figure out what the idea here is the same here. So let B be a vector. Well, what do I know about a typical vector in V? I know that I can write it as a linear combination of the bases. So I can do this. I can write where A1, A2, all the way up to AN are just numbers. So every element in V, namely this little v, can be written as a linear combination of the bases, right? This allows me to associate V, a vector, this is in some random vector space mixed in. I can associate this V to a vector actually in Rn. So and this is the key. This is what I mean by associate by foreign vectors. Given an arbitrary vector in vector space, these numbers here uniquely determine what V is, because V is uniquely a linear combination of bases. So I can forget about the spaces here and put it in terms of something in Rn by just reading these numbers here. This is the coordinate vector, so I can associate with V with this coordinate vector, which is actually an element of Rn. Also, as then if you look at of course, this linear transformation actually takes, here we go, here's the linear transformation. This takes V to W, so TV is to W, and so it also has a coordinate vector, but now in the basis C, right? Because this thing now lives in W, and so what you can do, you can take TV and you can expand it in terms of the basis over here, and you can write this coordinate vector. This is, of course, a vector of size n. It's got n rows, it has size m, but it's actually W. In fact, T of B now this is a linear transformation. So this is A1 TV1 plus A2 TV2 is A1 TV3M. That is, I can write out the sum and then pull out all the constants here. And so this is A1 TV1 and C coordinates plus A2 C coordinates plus AN yes.
How did you know that the transformation was C coordinates and not B coordinates?
Because it doesn't make any sense for it to be in B coordinates because the transformation ends you up over in W, where this is the basis here. So remember where you're going. Your input is on V and your output is TP. And TP is actually an element of W, right? And so it doesn't make any sense to talk about TP as some of these over here because you're actually in this different vector space where the basis are determined sequence. Right? So what you can do is if you look at TV and C coordinates, because the fact this is linear transformation, all you have to do is read the coordinates here, or well, you can pull up the constants A1 and then look at the effect of T on the basis vectors of V this way. And so this actually gives us the matrix that we need. So if you look at the image of V and C coordinates, this is in V and D coordinates, where M is matrix because you can actually, if you multiply this out, this matrix here, if you put a BB1, you will actually get this expression. Right? There we go. So the answer to our question is yes, we can find this matrix that transforms the B to W via this point. So let's look at an example. So I'm going to do this first. First example. So let's suppose that V is a vector space with basis B1, B2. So this is some three-dimensional vector space. And suppose W is the vector space given by the basis C1 up to C4. Where now, suppose you have a linear transformation, V to W, and we're going to build the matrix for this linear transformation. Notice that, let me point out here in this example that V is a three-dimensional vector space. This has got three elements in the spaces. W is a four-dimensional vector space because it's got four elements in its space. But this is not necessarily R3 or R4. This is just some random vectors. Now, let T that can be W be a linear transformation. And once again, I'm going to kind of point out that one of the useful things about linear transformations is all you need to know about a linear transformation is what it does to the basis elements. Once I know what it does, in this case, I've got three basis elements in the domain, right? B1, B2, B3. Once I know what that linear transformation does to my three basis elements, B1, B2, B3, I know completely what the linear transformation does. So I only need kind of three data points. So let's suppose that T B1, there you go. Suppose it turns out to be C2 plus C3 minus C4. Suppose the T of B2 turns out to be C1 plus C3. And suppose T of B3 is 2C1 minus C3 plus 5C4. And again, since anything in B is a linear combination of B1, B2, and B3, and so the linear transformation, now that I have this information, I know if you tell me any vector in this first vector space, I can tell you what the output is. Now, what is the matrix for this? Actually, I can give you a matrix in matrix, and let's just read it off this. What is TB1 in C coordinates? Well, this is the information that I need. It is, let me write it out explicitly in C coordinates. It is 0 times C1 plus 1 times C2 plus 1 times C3 minus 1 C4. Agreed? So where does B1 end up? It ends up with a C coordinate 0, 1, 1, minus 1. So I can interpret this way. Everybody agree? Let's see if I can read this one quick. What is C coordinates B2? One coordinate or 1 multiplying C1. 0 multiplies C2 in this case. 1 multiplies C3, 0 multiplies C2. So there's C2 coordinates for that. And finally, what should the last one be? 2, 0, negative 1. I agree. 2, 0, negative 1. So let's just mimic what we did over here. Our matrix should be right. It should be a 4x3 matrix, and it should consist of these columns. So this matrix And by the way, you can check this because, when you put in B1 and B1 coordinates, you have, the matrix 1, 0, 0, and that gives you the correct output for this. Okay, so let's do another example, kind of a blast from the past. Let's do one that's, again, not exactly RN, but something very much like this. Let's look at B. I'm gonna kind of rehash this example a couple of ways after this. And I'm gonna put the basis of this in 1 x squared. Remember what this is. This is all polynomials of degree 3 or less. And here I'm gonna let W equal P2x. And its basis here, I'm gonna let be 1x and x squared. Everybody okay? So, and here I'm gonna let the linear transformation like this. Your input is polynomial, and my output is going to be derivative. Right. So, for example, what does a typical polynomial look like here? A0 plus A1x plus A2x squared plus A3x cubed. And its output is A1 plus 2 A2x plus 3A2 plus 3 x squared. Notice my input is a degree 3 polynomial or less. My output is a degree 2 polynomial or less, right? And we've seen that this is in fact a linear transformation. Okay. Now, I am going to write this. I'm going to find the matrix for this linear transformation. So, what do I have to do? I have to find that of T on basis. The right and C coordinates. That's really what I got to do. So let's see what basis is. Let's see what the effect is. T of 1. What's the derivative of 1? 0, right? T of x is 1. T of x squared is 2x. And T of x cubed is 3x squared. Agreed? Well, now let's write this in terms of the C basis. Oops, I started in the wrong place. Okay, I'm going to write 0 as a linear combination of the C basis, 1x and x squared. How about 0, 0, 0? All right. 0 and 0, 0x plus 0. I'm going to write 1 in terms of the C basis. Well, that should be 1, 0, 0. Everybody okay? How about 2x? What's that in terms of the C basis? Yeah. 0, 2, 0. Right. 0 times 1, 2 times x, 0 times x. And how about 3x squared? So what is the appropriate matrix here? Represent this, well, you just put in columns. Everybody okay? Let me ask you this. What if this had been from P3X to P3X? Well, this is not a big enough base P3X, so I'd have to add another X cubed, right? But notice the derivative of all my basis elements never require an X cubed, do I? So what would the size of the matrix have been if I were going from P3X to P3X instead of P2X? It would be like that matrix, only there'd be another row. Everybody agree with that? And what would that new row be? All zeros. Everybody agree? Let me change this problem another way, actually. What happens if I do this? And I'm gonna test my answer. This is also a basis for P3X, right? And I'm gonna let C remain where it was. So my new B is certainly a basis for P3X. You can check that it's linearly independent expanded, no problem. And I'm gonna leave the other C alone, but I'm gonna let the linear transformation do the same thing, right? So again, I'm gonna have P of X, P prime of X. Same deal. How does this change the matrix at all? Well, we'll go through the same exercise. That is, just see what the matrix does to the basis vectors in the appropriate coordinates. So let's look first at T of 1, which is 0. Well, actually, all the crap's the same. Oh, no, it's not. I have a new basis here. T of 1 plus X is again 1. That's the same. Like the derivative of 1 plus X, derivative of X. Now it gets a little different. This is 1 plus 2X. All right. And finally, T uh, 1 plus. This is 1 plus 2X plus 3X. Now, to build our matrix, we need to write this in terms of C coordinates. I bet this is 0, 0, 0 again. And this looks like this is 1, 0, 0. What's this one? 1, 2, 0. Okay. And this one should be 1, 2, 3. So now our matrix should look like this. agree? Now, I want to check. I'm going to do a gut check here. What was something you'd like to take the derivative of? Polynomial 3 or less. 3. Anything you like.
I don't know.
How about x cubed, right? I am a simple fellow. Okay, the first problem is I need to write x cubed. That's my input. I need to write it in terms of my new basis here. X cubed is something times 1 plus something times 1 plus x plus something times 1 plus x. So it's squared plus something times 1 plus x plus x squared. Everybody agree with me? Now, you can set up a system of equations to figure this out if you still like, but I think that we can probably do a little Columbo here and figure out what to do. Because can anybody tell me what just right out of the gates what one of these coordinates has to be? This one has to be a 1 because it's the only one that's got an x cubed in it, right? And the equation's got to be 1. So now 1 by itself isn't a good answer because I've got this extra stuff. Can you figure out how to finish this off?
Negative 2. Or negative 1.
Now it's already x cubed, so let's throw in a couple of zeros here. Everybody agree with that? So in the coordinates x cubed, I can write this as 1. No, wrong way. 0, 0, minus. Everybody agree with me? Now let's watch this take a derivative. When I look at this matrix, this is 0, 1, 1, 1, 0, 0, 2, 2, 0, 0, 0, 3, 0, 0, minus 1, 1. This comes out to be the vector. This row comes this column, that gives me a 0, right? This row comes this column, gives me a 0. And this row comes this column, gives me a 3. Agree? But these are in C coordinates. So this is 0 times 1 plus 0 times x plus 3 times x squared. So I just had a matrix take a derivative in terms of a different basis. Okay, any questions on that? All right, so let me give you one more theorem here. So here at the problem, I'm gonna make a connection here. Your book, for reasons that I don't quite understand, also does this theorem. They only do it with respect to diagonal matrices, and they make some remarks later. I'm gonna just do this in general. Suppose, let's see, what are my players here? A, B, P, R, N, matrices. Would be the vertical. A and B don't have to be invertible, but P is. And suppose, so here's my big setup here. A is equal to P, B, N. that is A and B similar. That is to say, A is a conjugate of B and B is a conjugate of A as well. A and B are similar. Now, encoded in this is some pretty cool stuff. So let me kind of map this out for you. Let me the basis for Rn formed by the column B. Okay, before I go any further, let me make a quick gut check. You know what? If I give you a square matrix like P, n by n matrix, I know it's got n columns, but you know, not all matrices do their columns form a basis for Rn. But I know in this case it does. Anybody tell me what's the key operative thing? Yeah.
It's nearly.
Right. The key here is P is invertible, so it has to have n linearly independent columns. And if it's got n linearly independent columns in Rn, that's a basis, right? So the fact that the columns of P form a basis mean that P is invertible and conversely. So if B is this basis, then B is the matrix for the linear transformation T of X equals A X in B coordinates. Okay, and I'm gonna do a computation to show them why this is true. Yes,
So is that a kind of like person M?
I'm sorry.
Is that kind of person B different from the other B?
Yes, this cursive B is a basis. Let me make it even more cursive. Very honest. Yes, I use this B and this B because what happens is this B, regular B, is the matrix with respect to this basis coordinates for each transformation. So let me show you why that's true. And then I'm going to kind of show you the big picture of that. For this, that, B1, B2, Bn, B3, and this is the basis for Rn and having columns because that's what it said here that the columns P form the basis because P is invertible, and I'm going to take this to be a problem. So in particular, P I can write this way. So P P is the n by n matrix I obtained just by shoving these columns. Notice that let me make this observation. This means that B, notice that P times X and B coordinates is vector X. This is just a translation of, when I list the coordinates, the B coordinates here. So if I have B coordinates X1, X2, X3, this comes to be X1, B1, X2, B2, Xn, Bn, which is the representation of X in these coordinates, right? So this is just our usual coordinate change matrix. And let me also point out that P is invertible, so I'm also going to make use of this. So when you do P inverse of X, it changes it back to this coordinate vector. So now I think I've got enough stuff to go on here. Yeah. Tx equals AX. Then what I'm going to do here is I need to show that B is the matrix for this linear transformation in B coordinates. So let me massage this a little bit. And what I mean by this matrix for T and B coordinates, this is equal to X coordinates is equal to the matrix TB1 coordinates TB2 TB coordinates all the way up to TBN. Now, notice each of these TBIs is a TBI. So this is, so notice T times EX is A times X. So I'm going to replace each of these TBIs by ABI. AB1, B coordinates, A2, and B coordinates, all the way up to A and N. And this is because and this is inside thing. But now, recall also this identity here. Notice that A, BI, and B coordinates is equal to P inverse of what's in there. That's just using this identity. When you have blob inside B bracket, it's P inverse blob. So here's your blob inside of P, inside of B bracket, that's P inverse blob. So now I can go a step further and do this. AB1, the inverse AB2, the inverse AB Now, we're almost there. Because this is now. Notice that in a certain sense, I have a common factor of P inverse A here. And this is basically, this is just P inverse A. Comes the matrix B1, B2. I agree with that, because this multiplies through, and you get exactly this. Anybody know a name for this? That is correct. This is P at the start. So this is P inverse. And P. And what is P inverse AP? This is equal to B. Which is exactly what we show. Let me point out that this is equivalent to, since P is a variable, this means A is equal to P. Right, just multiply on this side by P inverse and that. But, yes,
So that last line, what we're trying to show.
right here, that's right, because what we wanted to do is show the matrix that you needed. The matrix here, and we look at the action on this matrix here that you needed is exactly the matrix. B. Remember what the theorem says, the B is the matrix relative to basis things descriptive. So let me draw a picture of this as well. Suppose so here's kind of an example. Suppose you have two bases. So here's what's actually going on. Let A be piece B. Matrix for T in B coordinates. And B equal, actually, let me call this B and C. Matrix for T and C coordinates. So in B coordinates, then you have the matrix B that represents the linear transformation. In C coordinates, you have another matrix, say C. And you have, we'll call this you guys remember this, our coordinate change. So what this means is this is what's going on here when you do this. Here's the matrix that you need in B coordinates. There's perhaps a different matrix that you need in C coordinates. And how are they related? Well, if you do this, so imagine doing this, take P, change your coordinates from B coordinates to C coordinates, then apply the matrix C, so you're now here, and then get back here, and how would you go from here to here? Do the inverse of this. Which actually is the change in coordinates from C to B. This is the same thing as doing B. All right, going here, changing coordinates, doing C, and then changing back is the same result as doing B. And that's why similarity is important, because C and B basically represent the same linear transformation with respect to different things. Okay, any questions on that? Okay, y'all cogitate. If there are any questions, let me know. Don't forget you've got a quiz due today at 5 o'clock, but there will be no quiz over the fall break. You guys have a good one, and come back, folks, together.